says that if G is not ESL2R or C, then the number of irreducible lattices in G of volume most V up to conjugation, so the number of conjugacy classes is finite. And so this is one finiteness theorem, and it's a very beautiful argument. In his paper, there is a mistake, so we only assume G is not SL2R. But the mistake is just misinterpreted via the local rigidity theorem. Also, he doesn't consider the case of irreducible lattices, which contains factor of SL2R and SL2R. But in my paper, I add the argument to this. And then after that, but this proof is very non-quantitative. So as we showed the following theorem. Sorry?
Mistake you said was Planck did not assume that. Is that what you said?
Yeah, in one paper we don't assume, and then Borel actually remarked about it in his paper. Borel proved similar finiteness theorem for SL2R and SL2C when you restrict to arithmetic lattices. And then he also remarked about one mistake. But the mistake is just in the assumption, there's no mistake in the argument.
So what is the finiteness theorem in SL2R?
In SL2R and SL2C, the same is true if you restrict to arithmetic lattices. And then the result, the corollary that I said, that under some assumption on G, so G is soon to be not.
So where exactly use the Archimedes theorem?
Oh, I didn't say anything about. So in
SL2R.
Yeah, but that's a different story.
It's completely different.
Yeah. So in essence, if G is not SL2R or SL2C, and also not SL2R square and not SL3.
But for other rank 1 things,
Yeah. Then we show that the number of G mod K manifold, so it's the same as torsion-free lattices of volume most V. This is bounded by V to the C. Some constant. Okay, so I just want to remark. So this is for very general results. Now, for if G is the isometry group of hyperbolic space, so SON1, then what we show in the joint paper with Shachar Moses, Alex Lubotsky, and Mark Burger is that, which was before my work. So we show that we showed this upper bound, and we also showed a lower bound of the same kind. So you cannot improve it. So it's bounded between V to the CV, and there's a lower bound V to the BV for some person, for hyperbolic range.
G-mod here, what do you write?
Sorry?
G-mod manifolds.
Yeah, these are S manifolds. S is G-mod K.
So you're saying in the hyperbolic case you have a lower bound, similar lower bound.
Okay, so let's denote this number.
Right.
Let's denote this number by rho S of. So for hyperbolic manifold, so this is the theorem Mark Burger, Alex Lubotsky, and Shachar Moses. We prove that for S equals Hn, and n is 4, rho SV is bounded between V to the CV and below by V to the BV. So, and B and C are positive number and V sufficiently large.
So your remark is that the one you said later, the lower bound.
Sorry?
So your remark is that in your theorem for all the other cases, you don't talk about the lower bound.
Yeah.
You only get the upper.
Yeah, okay. Yeah, and prior to this, there was a upper bound. Gromov also gave the upper bound for the same case for hyperbolic manifold, but Gromov proved before. Gromov proved before that rho of the hyperbolic space V is bounded by V e to the e to the e to the V plus n. So, okay, so
Yeah, this is.
it's also good. And it's also only hyperbolic.
Sir, for the lower bound, the known construction of lattices all are arithmetic lattices, right?
No. You can get a lower bound for the same lower bound for arithmetic and for non-arithmetic.
So that means that most of the, not most, or I guess most of the lattices are arithmetic in fact.
No.
How do you get the
No,
same
no, no.
lower bound? No, in hyperbolic real.
No, we have the same lower bound. In that paper, we proved the lower bound of non-arithmetic manifolds. We used the idea, we showed that the lower bound, we only counted non-arithmetic ones. And we used, okay, I don't want to get to it, but we put one. Now later, in 2010, we wrote a paper with Lubotsky, Bololepetsky, and Anel Shalev, when we consider the question of SL2R and SL2C, but only for arithmetic manifolds. And we proved the same result, but in that case, we actually showed the precise growth. So we got the precise constant for above and below, like the same constant. So this is the Adams paper in 2010 for arithmetic. So the same lower bound is for arithmetic and for non-arithmetic. But okay, I don't want to get into this. I'll just tell you the story. I also wanted to mention that, okay, for high rank manifolds, it's expected that the upper bound is not, should be much less. And there are works of Lubotsky and other people. They show that the upper bound is something like V to the log V. But the works always relies on the common cycle property and the general Riemann hypothesis. So in particular for SLNR, although it's expected that the upper bound is much lower, there are no proof for that because you don't have common sample property. It's not known. The concept is not known. So for some Myron group, this is still the best known, but it's expected to be smaller. Now, another thing I wanted to say is that the conjecture about homotopy, that not just the number of manifolds, but the homotopy type of a manifold is bounded linearly by the volume. This I don't think it can improve in any case. Also in higher rank, you cannot get better than linear. And actually, I will show you. I can prove that it cannot be improved. So I will explain it maybe in my last talk when I'm discussing Van Shabu. I'll show that there are evidence that you cannot improve the homotopy type. Okay, this was just some remarks about the previous lecture, and now I already start so I hope you don't mind.
No. I lecture like that.
Okay, thanks. So the second talk is about Margulis. So the same lemma as Aravinda referred to as Gromov-Margulis lemma. I don't know, most people call it Margulis lemma.
I think I only wrote it for the variable negative curvature also.
Okay.
By the Gromov.
Yeah.
Perhaps I don't
So
know. Even like
I think historically it's not clear. So the idea goes back to in Kasdan Margulis work, but we're always also 20 years, 30 years earlier in Zassenhaus work, and also much earlier in Jordan work. So so the same idea appeared a long time before, and I think the reason that most people call it Margulis lemma is because of Stilstone and Gromov, who really showed how to get geometric consequences. They call it Margulis lemma. I think so. But I think the common name is Margulis lemma. So, okay. So again, we have a group G, which is semi-simple, central free. We have S, which is G mod K, and it has a Riemann structure induced by the killing form. So it's fixed Riemann structure, in particular, there is fixed volume form, and again, I normalize the Haar measure that corresponds to the volume form. This is always my assumption. And G is a subgroup of the isometry group of S. In fact, it's a subgroup of finite index. It's exactly the group of the connected component and the finitely many connected components. So it's a subgroup of finite index. So G acts by isometry, and also G is also a linear group. G is, you can think of it as a subgroup of SLG R, where D is the dimension of G. The adjoint representation is faithful and embedded here, so it's a linear group. And for any element G, we denote by dg the displacement function. So dg at point x is how much g moves x. This is the displacement function, and it's a convex function. So Arvinda mentioned it in his talk. So dg is convex. And the reason for that is that, so what does it mean convex? It means that for any geodesic C of t, the map t, the real function, goes to dg of ct, is a convex real function. And the reason is, what is this? This is the same as the distance between C of t and G C of t. So these are two geodesic, and as we said, in non-positive curvature, the distance between two geodesic is convex function. So this is a convex function. Okay. So what is the famous Margulis lemma? I will first state it, and then I will explain in some details how to prove it, and then I'll state also some variants of it. So along the proof, I will say a few more things, because later we'll need some variants of the Margulis lemma. So the Margulis lemma. Says the following. So there exist two constants, epsilon and m. So usually when you speak about Margulis constant, you mean epsilon. In most applications, m is not important, but for us, m is also important. And of course, the constant depends on G or S with fixed symmetric space. So there exist two constants such that if delta is a discrete group, delta is generated by this element with epsilon small translation at x. So delta is generated by the element such that the displacement of gamma at x is less than epsilon. So suppose there is some fixed point x, such that I look at all the elements that move it by less than epsilon. Then,
This is S or X? Capital
sorry?
X. Capital X.
Oh, x is s.
Yes.
Suppose there is an element in the symmetric space such that the displacement of all the generators delta is bounded by epsilon, then delta is virtually important. More than that, it's contains a subgroup of index m, which is nilpotent, and it's more than nilpotent, it's contained then delta contains a subgroup n of index at most m, which is contained in a connected nilpotent Lie subgroup of. So the group of small elements, the group generated by small elements, it's almost up to index m is contained in a connected important subgroup. And connected important subgroup, it's a very strong information because by Lie theorem, for instance, you can conjugate it into the upper triangular matrices, at least inside GLDC. You can conjugate it. So you have a lot of information. So this is the Margulis lemma. And I will explain why it follows, but I also explain some variants of it. We will need some variants of it. And this is an extremely important lemma. It's very useful. So, but first, I think the first time it appeared in the history, it appeared as Jordan theorem. So Jordan theorem says that if you have a finite sub for any D there is M, such that every finite subgroup of S or D is C, it means an index M subgroup which is abelian. So for linear group can be finite and arbitrarily large, but they're almost abelian. So up to bounded index they are abelian. And that's what Jordan claimed, and the proof of Jordan theorem is exactly like the proof of Margulis lemma. And also, it follows from Margulis lemma, of course, because, okay, you could state Margulis lemma in greater generality. You can replace S by general manifold, or transitive manifold, and G by general Lie group that acts on its transitive. And your manifold could be, but it should act with compact stabilizer. But if your group is compact in advance, the manifold could be a point, a trivial point. And then you apply the same argument. And every finite group, it stabilizes a point, so it acts trivially, and then it contains a subgroup of index M, which is contained in a connected nilpotent group. But connected nilpotent and compact is abelian. So that's why Jordan theorem follows. But the proof of Jordan is also the same. So, okay, I will explain. Another thing that you can deduce from Margulis lemma is, one of Hilbert's problem in the beginning of the previous century was to classify the crystallographic manifolds. So manifolds which are manifolds which are locally flat. So Rn mod gamma, or gamma is the speed group of a Zone And Bibelbach proved Hilbert's problem was to show that every such manifold meets a finite cover, which is a torus. But you can argue, you can give a few-line argument and deduce it from Margulis' lemma. Why? Because if the symmetric space is Rn, and so Rn has this property that it has derivation, so you can look at it from far away. And Margulis' lemma tells you that there is some epsilon. But if there is some epsilon, then for Rn, every epsilon is good. Because if you have a group which translates by 1,000, elements that translate by 1,000, if you look from far away, this 1,000 is just epsilon. When you apply Margulis' lemma for Rn, then you don't need epsilon. Every group of isometry, there is some group of index m, which is in a connected important group. And now, what is a connected important group? You know what the isometry group of Rn, every isometry has some axis on which it translates. Suppose it doesn't have fixed points. So it has axis and it rotates in the orthogonal direction somehow. And then you do some simple analysis and you can deduce very easily Bibelbach theorem and also from Margulis' lemma. So this is a very useful lemma for many applications, and we will see other applications. Okay, so this was some propaganda for this lemma. If you want, after the talk, I will explain more about these consequences. But now, so why did it follow? So suppose, consider SLDR, consider GLDR, because we assume that G is a subgroup. Okay, and now let A and B be matrices which are close to the identity. So what does it mean? It means that A is identity plus A, and B is the identity plus B. I'm just doing a small computation. So, and A and B are small. A and B are, let's say, A is bounded by epsilon, and B is bounded by delta, and both epsilon and delta are small. So, suppose this is the case, and then I claim that if A and B are close to 1, then the commutator of A and B is much closer to 1. That's the claim. So look at the commutator. A, B, A inverse, B equals. And you want to estimate this distance. So first you can write it as AB minus BA times A inverse B. Just the way it's writing. Is it correct? Yeah. And then you can say that this is the same as AB, capital A, and BA. So these matrices are not invertible anymore. They're just in A and B are in MDR. So they're not invertible, but I don't care. They exist. And here I do A inverse B. And now we use the fact that the norm of matrices, first it satisfies the triangle inequality, like every norm, but it's also submultiplicative. So this is at most 2 times epsilon delta times the norm of A inverse and the norm of B inverse. But we can assume that this implies that the norm of A inverse is less than 2, and also the norm of B inverse. You know that inverse is continuous. Taking inverses is continuous in every topological group. So if an element is close to 1, then its inverse is also close to 1. In particular, the norm of the norm is less than 2. So it's less than 2, it's even less than 1 plus epsilon. But I don't care. So this will be at most 8 times epsilon delta. I don't care, 8 is a constant. So, for instance, if epsilon equals to delta, I start with two elements of distance epsilon for the identity. The commutator is of distance epsilon squared from the identity. So, let me summarize it. In the following way. So, for two sets, let's call it omega 1, omega 2, define the commutator omega 1, omega 2, but I do also this. It's not a group, it's a set of all commutator A, B, such that A is in omega 1 and B in omega 2. Okay? For two sets, this is the commutator. And you define omega 0 or omega 1 to be omega and omega n to be the commutator of omega with omega to the n minus 1. And the corollary is that corollary of the computation is that if omega is sufficiently close to the identity, sufficiently small neighborhood, then omega n will tend to the identity. So if, let's say, the corollary says that there exists an identity neighborhood, omega such that omega to the power n tends to the identity. In the sense that it will be eventually contained in every identity neighborhood. So the picture is this is G, and this is the identity, so this will be omega. So it will get smaller and smaller. So this is at least I explained the idea of this. You can find it in more details in Raghunathan's book. I like very much so that it's appeared in many places, but a very good reference to Raghunathan's book. And and then here is a straightforward corollary for this. Suppose that gamma in G, so G is a closed Lie subgroup of SLDR, and omega is the neighborhood, if you want, in SLDR or in G. Gamma is discrete, and gamma is generated by its intersection with this small neighborhood, for which the commutator stands to the identity. Then gamma is equal. So let's say that omega is not that it's not just let's suppose that it's relatively compact. It's not so important. After finding many steps, it always becomes relatively. But let's assume already that there exists a relatively compact Of course, if set has this also at this point. So I can take it to be relatively tall. And then this intersection is finite. And there is the proof of this. Okay, or the idea of the proof is that write gamma intersection with omega and look at the n power of this. This also tends to the identity. Okay? But this tends to identity inside a discrete set because gamma is discrete. So it must be the identity for large n. Yeah. This implies, because gamma is discrete, that gamma intersection with omega to the power sum n0 is trivial. And then you'll see that it's important. Why? Because to prove it formally, you say, okay, one step before it's trivial, it contains only elements which commute with everything. So it contains only central elements. Okay, now you divide by this and use some induction and you show that it's actually. So this implies, so some simple arguments show that gamma is important of Frank at most n. So that's the, and again you can find it in Nathan. And you can find actually a stronger state. You can actually do exactly the same, but instead of doing, if you restrict omega to an even smaller neighborhood, then in every Lie group there is exponential map, which is a diffeomorphism on small neighborhood of 0 of the Lie algebra, and it has an inverse, which is a logarithm map. Again, and a small neighborhood of identity. And if you restrict to a sufficiently small neighborhood on which the logarithm is well defined, you can actually play the same game on the Lie algebra. So for all the elements, you take logarithm, and then you do commutator, and you use the commutativity of the diagram for adjoint representation and logarithm and exponent, and you prove so I don't want to write the details. Again, I recommend you to look at the Nathan's book. It's a half-page or one-page argument. It uses the same idea, but applying logarithm and an exponent. And the result is the following theorem of Zas and House. Okay, now I'm in trouble because I have no idea how to spell Zas and House.
Double S E N H A U S S.
Yes?
I think one single S last one.
Okay. So the theorem of Zas and House, which in Latin we also refer to Petar Margulis because they proved they were not aware of Zas and House, so they proved the same results 30 years later. So the theorem of Zas and House is a bit stronger. So why is it better to do it for the Lie algebra and not for the group? Because for the Lie algebra, you will get an important Lie algebra. An important Lie algebra, it means that the exponent is a connected important group. And this is what we prove. Every Lie group, so here I assume semi-simple, and therefore it's center free, so it's a subgroup of SLN, but in general it's not a big price because every Lie group is locally isomorphic to a subgroup of GLN, because up to a central discrete kernel, so you can do it for every Lie group. So let's write it for every Lie group. For every Lie group, given a Lie group, there exists an identity neighborhood so people call it a Zassenhaus neighborhood. I will denote it by omega z. Z after Zassenhaus, such that if gamma in G is discrete, and gamma is generated by gamma intersection omega C, then gamma is contained in a connected nilpotent sample. This is Zassenhaus theorem. And you can now prove it. I gave you all the ideas. I mean, I didn't give all the arguments, but all the idea, you can prove it yourself, or you can look in Raghunathan's book and read it there. So I don't want to spend more time on this. And you see, this is already a big hint for the Margulis lemma. So still, it looks even better than Margulis lemma because there's no finite index. So why do we need a finite index? So the reason, so now I'm heading towards moving Margulis lemma from this. This I can do. This I will do with full details, but in Margulis lemma, okay, here I start with a discrete group that is generated, the generator lays near the identity, and I say this group is actually nilpotent and containing the connected nilpotent group. Here I start with a discrete group generated by small elements. So why can't I say this? The reason that being small doesn't mean that you are near the identity. Just means that your displacement is small. The displacement is small. It's in fact there are elements with displacement 0. If you are in K, in a compact group or in a conjugate of K, then you have displacement 0 somewhere. But it doesn't mean you are arbitrarily close to the identity. So the reason you still need to take a finite index and so where comes the finite index? Why then in the Margulis lemma we need to take finite index? We need to go to a finite index. So the reason is that that dg less than epsilon doesn't mean that you are close to 1, but it means that g belongs to a neighborhood, not of identity, but of a compact group. Right? Stabilizer of a point is a compact group. So if you fix a point, you're in a compact group. If you move it by less than epsilon, you're in the neighborhood of a compact group. So if this is G, suppose this is G is not compact, but let's suppose this is G, and here inside you have a compact group K. To say that the displacement is less than epsilon means that up to conjugation of the compact group means that you are in a neighborhood of A. This is a neighborhood of A, and of K. Now here you have the Zassenhaus neighborhood of identity is something that looks like this. It's a neighborhood of identity. It's not a neighborhood of K. But then you need to take finitely many translation of it and you will cover K. And this finite translation, when you translate it to a proof, it's what gives you this finite index. I will do it. So this is at least an intuitive explanation for this lemma. Okay, but when I prove the Margulis lemma, I will need more. Before proving the Margulis lemma, let me also say something about non-uniform lattices, arithmetic lattices, because so sometimes you want to know more. You want to know that your finite index subgroup is not just contained in a connected important group, but if delta is a subset of non-uniform lattices, at least you want to say that also it consists of unipotent elements, so that's a good information. So this is what I would like to do. So
Yes, the connectedness will. What's the kind of extra advantage it gives you?
sorry.
Getting a connectedness. What's the extra advantage it will give you so that you can conjugate it to the upper triangle or something like that?
It gives you that it's conjugated to the upper triangular inside, at least in GLDC, but it doesn't mean that it's contained of consists of unipotents. It may contain some same thing. But so now luckily Perlay in his talk yesterday told us a bit about the structure of arithmetic group. So I'm doing a side trick now and tell you that suppose gamma in G is arithmetic and non-uniform. So then you remember we assume that G is subgroup of G of SLD R, right? And we assume that where D is the dimension, so this embedding is via the adjoint representation. And in general, so Perlay explained yesterday that there is a rational structure on some extension of G, on some G times O, where O is some compact group. And there will be a rational structure there such that gamma is commensurable to the Z point. But as he also mentioned, if O is non-trivial, then the lattice gamma will not have a unipotent element, so it cannot be non-compact. So if gamma is non-compact, you don't need to take compact extension. So what does it mean? It means that gamma. So it means that there is a rational structure on G. There is a rational structure, Q structure, such that gamma is commensurable to GZ. So there is a Q structure on. So G is a algebraic group defined over Q. In other words, you can conjugate G inside SLD-R such that the group after conjugation is algebraic over Q, and gamma is contains a subgroup of finite index which is inside SLDZ. Now, if you play a bit with the arithmetic group, then you know that if you commensurable to SLDZ, you actually conjugated it to SLDZ. To be in SLDZ means that you preserve some G lattice in RD. And if you commensurable, it's also means that you preserve some other D lattice, so other Z lattice. So this implies that actually gamma is conjugated to a subgroup of GC or GZ, or if you want SLD. Why is this good? Because now we know that if I look at the characteristic polynomial of any element here, then it's an integer coefficient. Characteristic polynomial doesn't change when you do conjugation. So let me write it. The corollary of this reasoning is that, or if you want a fact, is that the characteristic polynomial characteristic polynomial P gamma of x of every gamma which belongs to a non-uniform arithmetic lattice the characteristic polynomial is integral. So P gamma of x belongs to Z of x. So it's a conic polynomial, but it's integral. It has integer coefficient. Okay. Okay, so if it's integral and gamma is close to 1, then the characteristic polynomial must be close to 1. But if it's close to 1 in a discrete set, it's so the corollary, there exists an identity neighborhood let's call it omega u of unipotent, such that if gamma is in G is non-uniform arithmetic, then gamma intersection with omega u consists of unipotent. Okay, so we call that a unipotent element is an element such that all the eigenvalues are 1. 1 is the only eigenvalue. Or in other words, that the characteristic polynomial is the same as the characteristic polynomial of the trivial matrix. And if you close to the identity, the characteristic polynomial must be closed, and if it's integral, so you see why it's right. Okay, so this is the advantage that we have for non-uniform. So now we're going to prove the Margulis lemma. So first, after writing this, so see, okay. So, or maybe actually, okay, let me say it. Now, and so proof of the module step. So first, also this Zassenhaus neighborhood, and also the new neighborhood of omega u. If you have such a neighborhood and you conjugate it, you get another neighborhood with the same property. So once you have one, you can conjugate. So it's and also in other words, in the Margulis lemma, we said that a priori there exists x, but such that blah blah blah. But since G acts transitively in the symmetric space, I can fix x and suppose that my group generated by element with small displacement is fixed x, right? So it's the constant that I'm going to get are independent of x. That's just a remark. Okay. So let's start like this. So let U be an identity, a symmetric identity neighborhood. Such that U square is contained in omega z. So this will be sufficient just to prove the Margulis lemma, but let's assume that it's also contained omega u, and then we will get something stronger for non-uniform lattices. I don't care. I just take smaller neighborhood. So suppose that now let's fix x a point in the symmetric space, and I'm going to look at. I'm going to assume that my discrete group generated by small element with small displacement at x naught. And as I said, because the action is transitive, it's okay. Fix and define M to be the volume of, okay, I look at the set of all G in G such that the displacement of x naught is less than 1. This is a compact set. It has finite volume. I multiply it by U. It's still relatively compact, it has finite volume. And I divide this by the volume of U. This will be so, and I want M to be an integer, so I take an integer which is bigger than this. first integer. So this is how I define M. This will be M in the, this will be the index in the matrix. And now I need to tell you what is epsilon. Epsilon will be 1 over. And now, why the proof? Okay, so now I have a discrete group. Suppose delta inside G is discrete, and delta is generated by a sigma, where sigma is the set of elements gamma and delta, such that the displacement of gamma at x, the special point, is less than x. Now epsilon is equal. And I'm claiming that delta up to index m is contained in a connected equation. Okay, so so I tell you exactly what is the connected equation group. So set n to be delta intersection with u squared. So you see, u squared was contained in a Zassenhaus label. So n is contained in a connected important group by Zassenhaus theorem. By Zassenhaus theorem, n is contained in a connected important. Okay, so I have to tell you why n has index at most m in delta. So this is exactly the argument that here was intuitively explained, and now formally so suppose, by way of contradiction, that delta mod n is greater than n. So with at least n plus 1. So you look, see, delta mod n is you think of it as a Schreier graph. So it's it's Schreier, like a Cayley graph. So you have the generator sigma. Like Cayley graph, there is also a Schreier graph and a single quotient. So if this graph has at least n plus 1 vertices, if a graph has n plus 1 vertices, it means that also the m ball, there is a specific point here. The point corresponds to the trivial quotient. And now, suppose that this graph, so this is some graph. This is the Schreier graph of this group, delta mod n, which at the moment I don't even know that it's finite. And if this graph is more than m epsilon, more than m elements, then also the ball of radius m is more than m elements. Why? Because you show it by induction. The ball of radius 0 has 1 element. The ball of radius 1 is bigger. The ball of radius 2 is even bigger. So it always grows by at least 1. If at some point it stops to grow, it means you covered all the graph. But you assume that the graph is more than. So in any case, the ball the M ball, mth ball around the trivial coset, the trivial coset has more than m plus 1 elements. If we assume the control, right? Okay, but what is this M ball? It's the element of the M ball are elements which you can express by words of the element in sigma of length at most m. So these elements, so the M ball, let's call it B M sigma. Okay? In this triangle. But for any gamma in B M sigma, the displacement of gamma at x naught, is at most m times epsilon. Because gamma is written by a word of length m in the generator. All the generator has displacement at most epsilon. So you conclude that. This is at most 1. So you deduce that B M sigma is contained in the set. Let's call this set by name. I don't know. Let's call it A. It's contained in A. Also, the assumption was that all of them represent different cosets of n, because there are different points in the triangle graph of gamma mod n. But look, m was, so we have more than m elements, so the assumption of m, which is written here, the assumption on m, the definition of m, implies there are gamma 1 and gamma 2 which are different inside the ball of radius m in sigma, such that gamma 1 u intersect gamma 2 u non-trivially. Why? Because if they were all disjoint, we will have m plus 1 disjoint copies of u inside this set. But it's impossible. If they were, right, they cannot be all disjoint. But this implies that gamma 1, gamma 2 inverse belongs to u squared. We call u is symmetric. But u squared is inside n. So that they don't belong to a different coset. Okay. So this finished the proof of modulus then. So I did it a bit fast, but all the details, and also this argument you can find very similar in Searson's book, Three-Dimensional Geometry and Topology. Now, so this finished the modulus lemma. what about the non-uniform arithmetic case? I didn't say anything about it yet, except that this
You
use.
use the neighborhood.
Yeah, I use the neighborhood. So in the non-uniform arithmetic case, we also deduce that that my subgroup N. So in the non-uniform arithmetic case, the non-uniform arithmetic case, we also deduce that N is generated by unipotent. You remember N defined as a group generated by intersection with delta intersection with U square. U square was contained in omega U. If we're in omega U and we're a non-uniform arithmetic group, then we're unipotent. But N is connected, it's a connected nilpotent group. So it is conjugated inside GLDC to the upper triangular matrices by lithium. And if it is generated by unipotent, then it consists of unipotent. Because you see that on the diagonal you get only 3 elements. So as a corollary we get the following result, we call it lemma. Again, if gamma is non-uniform arithmetic, then for every x in S, let's write it as gamma epsilon. Gamma epsilon x, it's the group generated by gamma in gamma such that its displacement is less than epsilon. Admits an index M subgroup which is contained in a connected unipotent. So this is the results for non-uniform that I will use when proving the homotopy type. Okay, I have 15 minutes, so let me just give an even stronger result for non-uniform arithmetic. Again, I'm referring to Raghunathan's book. Maybe you know there is a classical results of finely generated linear group of a field of characteristic 0, saying that every finely generated linear group admits a finite index subgroup which is torsion free. So it's called Seldon lemma, although it was probably known before. In Koch's casing, proved something like that. But in Raghunathan's book, there is a stronger statement which is better. So definition. A matrix is called a net if the eigenvalues of it are not root of unity or moreover, if the group of real elements, the group generated does not have a finite order element. So they're not a root of unity, does not have Tholen. So does not contain roots of unity. So it's a subgroup of the multiplicative group of C. So, and then Raghunathan proved the following lemma in his book. And a group is called a net. A group is a net, a group of matrices, linear group, if every element is a net. Does not contain, non-trivial order. And then there is the following lemma, which appears in Raghunathan's book, that every finitely generated subgroup, every finitely generated linear group over C, over field of zero characteristic, generates subgroup of GLDC admits a finite index subgroup which is an X. So there is a finite index subgroup which doesn't contain eigenvalues which are root of unity. What does it mean? It means that in particular it's torsion free, but now let me deduce a stronger result for so recall that this question. So recall that if you have a non-uniform arithmetic lattice, then it is, we think of it, the adjoint representation of it is contained in, after conjugation, in SLDZ. SLDZ has a subgroup of index, K, which is a net. So then the original group is also a mixed subgroup of index K, which is a net. So corollary, there exists K, depend on G, such that every non-uniform arithmetic lattice gamma admits a net subgroup of index most K. Right? This is K. So, what will be the Margulis lemma for non-uniform arithmetic net lattices? So let me just state it again. So I think this answers the question I think Perley asked in Arvinda's talk yesterday, that if in some cases you don't need to go to finite index. So in this case, so if gamma inside G is non-uniform arithmetic and a net, and as the corollary here said, it's just you don't pay a big price to go to the situation, then then gamma epsilon x, for every x, of course, gamma epsilon x is contained in a connected unipotent. In that case, you don't need finite index. And what is the proof? By the previous lemma, we know, by this lemma, we know that there is a subgroup of index M which is contained in a connected important group. So, if you take any element in the okay, so let me write it. So this, I didn't write it in this way in my paper, so let me write it. So, so proof by the previous lemma gamma epsilon x admits n of index most m such that n is contained in a connected unipotent, Now, I claim that gamma epsilon itself, must be actually contained in n. And why is that? If gamma is inside gamma epsilon, then gamma to some power, or let's say m factorial, is contained in n. But n in a connected unipotent, I call it n tilde. So it's contained in n tilde. So it means that gamma to this power is unipotent in particular. But this means that gamma itself is unipotent. Because otherwise there were eigenvalues which are root of unity. This means so gamma to this power is unipotent, and this implies that gamma is unipotent. Now, unipotent group, it has a property, so this is connected unipotent group. If an element is unipotent, every unipotent element is contained in a well-defined one-parameter unipotent group. The one way to see it is take the logarithm. So for nilpotent element in the Lie algebra, the exponent is a polynomial, and the logarithm is also polynomial for unipotent, which is inverse to it. So there is a diffeomorphism between algebraic diffeomorphism between the Lie algebra of a nilpotent group, for unipotent group, and the unipotent group. And if you have a unipotent group, look at its logarithm. It's well defined always, a polynomial, and then look at the span of it, the z span of it in the Lie algebra. Take the r span of it, then you get a line in the Lie algebra, and take the exponent, which is again a polynomial map, and you get a one-parameter unipotent group in G, which is well defined and contains your element. So it's single, well-defined one-parameter unipotent group that contains every unipotent element. There is a well-defined such an element. If you replace the element by some power of it, you get exactly the same unipotent group. So so this power fit, the one parameter unipotent group must be contained in M tilde. But it's the same one parameter unipotent group that corresponds to gamma. So gamma also is in M tilde. And this implies that gamma is in M tilde. So I did it in hand waving, but if you want, I can repeat it. For those who want, it's because
This gamma might be semi-simple times when you put it on semi-simple power, mth power may be identical.
no, because gamma is a net.
Ah.
So there are no rules of unity.
Okay.
So if a power of you, if you take a power and is
Yeah,
unipotent, then okay. So on one hand, I'm happy about this lecture because I finished all the things that I will use later. Using Margulis lemma, I'm going to use this last lemma that I stated. On the other hand, I also wanted to explain to you some relation to geometry and fixing decomposition and of rank 1, but there was no time for this. So if you want, I can continue for 10 minutes to describe, or if you want, maybe it's not so.
For me, it's okay. Fine, please go ahead.
So this is
as long as it's okay with you.
yeah, for me it's okay.
Fine.
So as I said, the Margulis lemma is really exciting, and I mentioned application to Jordan theorem, Bieberbach theorem, all of them follows easily. Another application, which is a classical application, is the fixed in decomposition. And this also explains the idea related to homotopy conjecture. So, and this is ideas of Stilson.
Is this also used by Kasdan Margulis proving unipotence in non-uniform lattices? Silver.
Well, of course, they use similar ideas. Yes, but they don't, in the proof, so the Margulis results, they don't really need to go through Margulis lemma. They take a different path. Yeah, I'm going to give you, in the third lecture, the next lecture, I'm going to give an alternative proof on Margulis theorem. And I will use Margulis lemma. So it's, in a sense, it's more elementary than their proof. But the original proof didn't use Margulis lemma. It used Zassenhaus theorem. Okay, so the fixed in decomposition. In rank 1. This is very classical. It's idea of Stilson. But first, maybe before saying that, let me repeat something that Ravinda said yesterday about classification of isometries. So I mentioned, I defined the displacement function. So there are 3 types of isometries. The 3 types of isometry. Now I'm speaking of general symmetric space, or in general Hadamard manifold, not necessarily Hadamard. One is when the displacement dg attains when g g admits a fixed point. So first you define the mean set is the set of all x in S such that dgx is the infimum of this function. And this might be an empty set. So first type of isometry is elliptic, is when g admits a fixed point. And then mean G is exactly the fixed point. G. The second type is hyperbolic, where this means that mean G is non-empty, but the displacement is always positive, so the infinite is bigger than zero. So it attains the minimum, but the minimum is positive displacement. And the third is parabolic. And parabolic means that the mean set is empty. Okay. That's parabolic elements. So there are three types. These two types are semi-simple. So in the Lie groups, these are exactly the elements that can be diagonalizable over C. And these cannot. In rank 1,
And is it true that this elliptic will correspond to compact elements and hyperbolic?
yeah, elliptic are exactly elements which contain in a compact group.
And hyperbolic is R split.
Hyperbolic, they're not necessarily R splits. They could be composed by maybe they
It is not all of
yeah, but maybe they may not be completely split, but
But they will have a
they will have real eigenvalue. Yeah, they will have they're not R split necessarily, but they will have and parabolic are those which are not semi-simple. Okay, it will take a lot actually to be very precise, but at least in rank 1, the parabolic are also unipotent. So they have when you're unipotent, the minimal displacement does not attain, but the infimum displacement is zero. So when you approach the fixed point at infinity, the displacement goes to zero. So in rank 1, so remember we define if M is a manifold and epsilon is the Margulis constant. And then we define M less than epsilon, set of all x in M, such that the injectivity radius at x is at most epsilon over 2. So if you look at the universal color, there is an element in gamma in fundamental group that moves it by at most epsilon. And the thick part is the complement. And Finston used Margulis' lemma to tell you exactly what is the thin part. And it's not hard, it's half-page proof. I could do it in 5 minutes, but if I had 5 and 5 and 5, so let me write it and maybe not explain all the details. So here is the fixed in the composition. If rank S is 1, so it's negative curvature, and the volume of M is finite, then let's say m less than the thin part, the epsilon thin part, m epsilon, has at most some constant times volume m components, each of them which splits onto, which has of, and there are two possible types of two possible types. One, a tube, a tubular neighborhood of a short geodesic. This is topologically a ball bundle over a circle, and it's a tubular neighborhood of a short geodesic. A cast, and this is of the form n cross r plus, where n is some compact one dimensional manifold. Okay, here D is the dimension of S. Previously I used D to say the dimension of G, and now I use it for the dimension of S, so it's
D.
okay. D now is the dimension of S. Until now it was the dimension of G, which is not the same, but okay. So this is the 16 decomposition. The picture is as follows. Let me just explain the picture.